The specifications of the soccer robot are stated in the EGB320 F180 rules and are as follows. The robot must not exceed the max diameter of 180mm and the max height of 150mm. The ball must not be able to enter the robot in any way, referring to the 80-20 rule. Also, the budget must not be able to exceed $165 for omnidirectional robots. It must be able to detect the ball, obstacles and goals, and it must also be able to move to the ball, dribble it and kick it into the goal while having the ability to avoid obstacles. Also, the soccer robot must be able to find the ball if it is initially occluded. Additionally, all components must be integrated to be able to score goals at a consistent rate. Now the team will talk about each of their individual subsystems of the soccer robot.
The kicking mechanism is used to kick the ball into the goal upon approach at a speed of 2.5 meters per second. A 24-volt linear push-type solenoid with a T-shaped kicking plate weighted to match impedance with the ball was deemed most efficient. This was positioned underneath the chassis between the wheels, ensuring that the ball is hit at the center and the dribbler isn't interfered with. The purpose of the dribbler is to produce backspin on the ball for control, allowing it to be moved around the field. The dribbler piece was 3D printed into a hyperbolic curved notch dribbler, which was coated in rubber bands. It was positioned to contact the ball at the highest point possible for optimal ball spin. A gear system was used attached to a high-speed, low-torque motor.
I'm Danny and I was in charge of the drive system. The drive system is critical for our robot to effectively maneuver about the playing area. We decided upon an omni-drive system as it allowed us to maneuver the robot in any desired direction. DC motors were carefully selected to have sufficient amounts of torque at low RPM to achieve a minimum constant velocity of 0.05 meters per second and be capable of achieving maximum velocity of 0.3 meters a second. I chose Hololoom plastic gear motors as they fit our motor requirements and didn't blow our budget. In order to control each motor, I used two L293D H-bridge motor drivers. Forward and reverse operation of each motor was achieved using digital pulse width modulation from the Raspberry Pi GPIO pins. The motor drivers were also shared by the dribbling system. The wheels were the most critical part of the drive system. Several 3D printed designs were prototyped, but due to errors with the print quality, we ultimately decided to go with purchased omnidirectional wheels.
Hi, I'm Cody and I'll talk you through the design of the vision system used in the soccer robot. What you're seeing is a video capture of the image segmentation in action as the bot seeks out the ball and delivers it to a goal. Image thresholding was done in the HSV color space without morphology, instead using size, geometry, and location thresholding to remove noise. The image was then segmented using OpenCV's library to draw bounding boxes and circles and find their sizes. The wall was segmented without form and instead the lowest and therefore closest point of the raw contour was used. The bounding boxes were then printed to an image and displayed, and dots were placed at the bottom center of the object, which represented its location. This point was then mathematically converted to distance and bearing and then passed on to the navigation system for each object. Note that while searching for the yellow goal, the blue goal was not segmented, and vice versa. This was done to speed up the vision system to achieve target FPS and with minimal latency.
Hi, I'm Isaac, and I created the AI navigation system for our soccer robot. To create the AI navigation component of the robot, I applied the Artificial Potential Field, or APF for short, approach. Basically what APF does is it assigns each object within a system a value. This value determines a vector force, and ultimately the forces of all objects within view are combined to give a direction. This direction is consequently used to determine which motors are turned and the speed and direction in which they turn. Initially, the goals were ignored as the ball collection functionality had to be created first. The ball was given an attractive force, so the robot would try to get the ball. Obstacles were treated as the opposite of the ball and were given a repulsive force. Once the functionality for both the ball and the obstacles were created, an attractive force was applied to the goals, depending on which goal was the target and if the ball had been collected. If the ball was initially occluded or not in view, the robot would rotate in search of the ball. If it couldn't find the ball after one revolution, it would make its way to the yellow goal area and look around there. If it still couldn't find the ball, it would go to the blue goal area and look around there. Unfortunately, sometimes the robot left the ball behind as it didn't get picked up in the dribble. In addition to this, our kicker system failed, so the robot had to push the ball into the goal.